Okay, welcome back everybody. Just wanted to see where we were on the syllabus because we're entering a new phase of this class. Now that we have stellar evolution and Einstein's relativity under our belt, we can start to talk about the origin and nature of the universe itself. And what our plan is today, what we're going to do is talk about the origin of the universe and why we even know there is one. Because the data suggesting that the universe had a beginning is pretty compelling. Then I'll introduce the activity that's due on Thursday called the expanding universe, where we're going to use a balloon to build our own universe and illustrate how the universal expansion causes the motions of the galaxies that we see in the sky. And then we're going to move on to some pretty striking observations of galaxies indicating that about 90% of the universe is stuff we can't even see. It's called dark matter. We'll talk a little bit about our own galaxy and its formation and how we know about its shape, and then we'll move into modern cosmology, total structure of the universe, and then talk about the burning question, which is where the heck is everybody? Are we the only intelligent species in the universe, or are there more out there? So that's the map for the kind of third part of this course that we're going to be going over today. What I'd like to do is start off with a discussion about why we know the universe had an origin, because this is something that we've discovered over the last 100 years or so through very, very careful observations. And just recently, in fact, only a few days ago, scientists discovered even more evidence for the early universe's beginning as we're going to describe it today. So this is an ongoing exploration. It's stuff we have lots of evidence for. We keep getting more evidence for, and I think it's important to understand where all this comes from. So what we're going to do today is just talk briefly about the origin of the universe and the evidence that we have to support that, and then we will move on to trying to figure out how this plays out in the motion of the galaxies. So you've probably all heard about this thing called the Big Bang, and the Big Bang is what scientists, in my view, unfortunately call the origin of the universe, namely because it wasn't terribly big and it wasn't a bang. That name was given to it and almost as an afterthought, because when it was first proposed, it was kind of tossed aside as that silly Big Bang idea. However, what I'm going to show you today is that the evidence is very compelling that we have an origin that is described by this theory of the Big Bang that we'll talk about. But first of all, I just want to talk about the evidence for an origin. How do we know the universe had a beginning? It's not a foregone conclusion. If you imagine a universe, I can imagine one that's been around forever, that is static and immortal and has been infinite in extent, infinite in time, and it's always been there. In fact, if you look at a lot of the creation stories that are told by populations all over the planet, many of them have this as their central tenet. The universe, at least as a stage for planets like the Earth and people and things like that, is just this static, infinite expanse that then planets get created and people get created and things like that. What I'd like to do, though, is point out that there are 4 pieces of evidence that the universe had a physical origin in space and time. And the first one is that when you look out into the universe, all of the galaxies are moving away from us. Now, this was an observation that was made by Edwin Hubble back in the early 1900s. And what he did, and we'll do more of this when we talk about our little experiment we're going to do later, what he did was he observed the recession velocities of the galaxies using the Doppler effect and compared that to an estimate of their distance. And he found that the further away a galaxy was, the faster it was moving away from us. And he made a plot of that velocity versus distance, and you can see the velocity. Let's talk a little bit about the units here. Velocity is measured in kilometers per second, so this is the recession velocity measured from the redshift. And the distance is in something called megaparsecs. So that's 10 to the 6, or 1 million parsecs. And if you remember, 1 parsec is equal to about 3.2 light years. So these things are really far away. And he didn't have a very good way of measuring the distances to galaxies, but we did know the distance to the nearest galaxy, the Andromeda galaxy. He made the generalized assumption that all galaxies were the same size, and if you assume all galaxies are the same size, then that gives you an estimate of their distance. And he made a graph that showed that the farther out you are, the faster you happen to be going. So if I pick a particular galaxy like this one, I'm out 100 megaparsecs. I'm going 7,000 kilometers per second. If I move into 40 megaparsecs, I'm only going 2,000, and so forth. So there was this linear relationship, and this was called the Hubble Law. And I can write down that linear relationship just saying that the velocity is proportional to the distance. Okay, so the velocity is equal to some constant times the distance, and in this plot that constant is about 67 kilometers per second per megaparsec. And we'll come back and talk about that a little bit later as well. So this was interesting because there's really only two possible explanations for this. One is that we are at the center of a giant explosion and the galaxies are flying away from us. Or if space and time itself, which we now know to be stretchy, is expanding, then that will make it appear as if all the galaxies are moving away from us. Now, the first explanation violates what's called the Copernican principle because it puts us at the exact center of the universe, and there's no reason to think that we would be at the exact center of the universe. So throwing that one aside for philosophical reasons, the expansion of the universe appears to be the best piece of explanation that we have. So this expansion tells us that we had to have an origin, because if it's expanding away from us now, if we turn the clock back, it's eventually got to be compressed, and that means it had to have a beginning, right? Because there had to be some point where it was basically infinitely compressed that it started from. Now, keep in mind, this is why I think the Big Bang is kind of a bad name for this, because the entire universe could still be infinite in extent. You just make it infinitely dense. So you can have something infinite in size that's infinitely dense. So any particular region of space that you chose to look at would get smaller, but the whole universe itself is infinite in extent. It just happens to get denser and denser and denser. That origin, where it's basically infinitely dense, is what we call the Big Bang, the origin of space and time. So this observation of the expansion of the universe tells us that there had to be an origin. Now, this was shocking to Einstein because if you looked out at least the stuff in our galaxy, everything seems pretty static. It's not moving away from us in our galaxy. And in his equations for general relativity, he predicted the expansion of the universe, but he put in a little fudge factor because he didn't think the universe was expanding. If he had talked to Hubble a little bit, he would have found out that our observations indicating that it was. But at any rate, Einstein's theory predicts this expansion as well. Okay, so that's number one. Number one is the expansion of the universe. The second one is something known as Olbers' Paradox. Now, Olbers' Paradox is, it goes like this. If the universe is infinite in space and time, and I look out into space, ultimately, my line of sight should eventually hit a star, because even though the speed of light is finite, there's an infinite amount of time for the light to reach us. So that means that if the universe is infinite in extent, then in every direction there has been time for starlight to reach my eye. So I would predict that the sky should be bright, because every direction I looked, I should see starlight. However, that is not what we see. This is what we see. This is the Hubble Deep Field showing the dark space between the galaxies. This is as deep as we've ever looked into space. And just to point out some interesting things about this picture, anything that has a little cross on it is a star because it has a diffraction pattern from the telescope. But if it doesn't have that, it's not a star. So in this field of view, I am counting 1 star, 2 stars. Okay, there's a star there. So every single one where you've got a cross is a star. So there's only 3 stars in this field of view. Everything else in this field of view is a galaxy containing billions of stars. So this is a pretty staggering image, and this is as deep as we've ever looked in the visible spectrum, and the sky is still dark. There's still dark, empty space between the galaxies. So what this is telling us, well, there's really a couple of explanations for this. You can think about it like, here's an analogy. Imagine you're in the forest, right? And you look out in the forest, and if you're deep inside the forest, and the forest has been around forever, then everywhere you look, you're going to see a tree. And this is the analogy to what we should see if the universe is finite in extent, infinite in extent and infinite in time. However, if you happen to be at the edge of the forest, even if the forest has been around forever, you will see blue sky through the trees. So one possibility is we could be at the very edge of space. However, we look in every single direction, and this is what we see. So if we were at the edge of space, we would see white sky in one direction and dark sky in the other. So there's no indication that we're at some edge. The other explanation, since it looks the same in every direction, that we could be at the very, very, very center of a finite universe. However, again, from Copernican's principle about there being no special place in the universe, that's unsavory. I mean, I guess we don't have any direct evidence that that's not true, but it's unsavory because we've never found it to be true. The Earth is not at the center, the Sun is not at the center, our galaxy, we're not at the center of our galaxy. Why would suddenly everything be centered on us? So those two explanations we kind of throw out the window. The only other explanation is that it has taken time for the light to reach us, and the light hasn't reached us yet, right? So there are stars in every direction. There stars infinitely distant in every direction, but the universe has a finite age, and therefore the time hasn't elapsed for light to reach us. Break this sort of thing down by looking at whether we can have a finite or infinite universe in space and time, right? So these are our options here. Our options is that we have finite space and infinite space, and we have finite time and infinite time. And we can rule out the finite space because of the Copernican principle and the fact that we're not at the edge of the universe. So I can rule this one out, that anything in here that has finite for space I can rule out, right? Okay, so then I look at these two things and I say, well, the universe can be infinite in space, right? Then we have two options left. We have finite time or infinite time. But again, if we had infinite time, the sky would be white, so we can rule that guy out right there. And the best option we have is that we live in an infinite universe with finite time. In other words, we live in an infinite universe that has an origin. Now, the reason I kind of quibbled about ruling out finite space is because the universe could be really, really, really big, but finite, and we've just never seen the edge of it yet. That's a possibility. But for all intents and purposes, we've seen as far as we're going to see into the universe, and we've never seen an edge. So I would rule out, practically rule out a finite space. So by looking at just the fact that the sky is dark, we can infer that there had to be an origin, and the universe is really, really, really big, effectively infinite. So there's two pieces of evidence that the universe had an origin. Now at this point, I would be pretty compelled to accept the suggestion that the universe had an origin. However, we have even more evidence. And that other pieces of evidence include something called the cosmic microwave background. Now this is something that we need a little bit of physics to understand why we expect to see this thing called the cosmic microwave background. We have this universe that we, because of these two first pieces of evidence, are suggesting that was denser in the past, right? It's expanding, so if you turn back the clock, it had to be denser in the past. And we know from physical experiments that if you take any material, gases, particles, whatever, and compress it, it's going to heat up and the pressure is going to increase. So when we go back in time in the universe, it's getting hotter and denser and hotter and denser and hotter and denser. And there comes a point at the origin, near the origin of the universe, where the universe is so hot and dense that it's effectively opaque. It's almost like the surface of a star. The light, any light that's traveling around in the universe is getting absorbed and re-emitted and absorbed and re-emitted by other particles, and it's not flying freely through the universe like we experience today. And at that point, the universe has a particular temperature as if it was the surface of a star. Well, because when we look out into space, we look back in time, if we look far enough back in time, we should be able to see the afterglow of this opaque period of the universe. And this opaque period of the universe is called the cosmic microwave background, and because it's taken time for the light to reach us and the universe has cooled off, the temperature of this spectrum of light is much, much less. It's not 3,000 degrees Kelvin like we would predict early in the universe. It's only 3 degrees Kelvin, but we still should see it. So we see it in the microwaves, and it was first accidentally discovered by people building radio receivers when we first started doing radio technology. They pointed their receivers at the sky, and they heard this hiss that went away when they pointed it at the Earth. So we detected this cosmic microwave background, this sort of radio hiss of the universe, and started building better and better instruments to study it. So now when we look at the cosmic microwave background, this is what we see. Now these images here, just to explain what we're looking at, this top image, if you imagine sitting on the Earth with a microwave receiver looking at the sky, and we look at every single bit of the sky, and then we project that out in a map with the galactic plane at the center. So this is the plane of our galaxy, and you can even see some cool spots, or hot spots and cool spots in our galaxy. So this is the plane of our galaxy, and you can see that the sun has some motion in the galaxy. So we're moving towards one side of this thing and away from the other, so it makes this appear blue shifted and this appear red shifted. Okay, so we have to subtract that motion out. The second picture subtracts that motion out and just leaves the plane of our galaxy. So here's the plane of our galaxy, and you can see this afterglow in the microwave all around here. And then if you take out the contribution due to the galaxy, you're just left with this bottom picture right here. So this is called the cosmic microwave background. And what this is a echo of the time when the universe was hot and dense. And it's everywhere in every direction. It's also incredibly uniform. You can see there's some fluctuations here between the hot and cold spots, but these fluctuations are like 10 to the minus 6 Kelvin, right? So they're milli to microkelvin variations. The WMAP one that we just launched back in 2001 shows a much finer detail, but still this uniform afterglow of the time when the universe was hot and dense. So this is something that was predicted by the Big Bang Theory. It was discovered and analyzed in detail using microwave instruments, and is the best snapshot we have of the birth of the universe. We're literally seeing light from the origin of the universe. Now, there's a couple pieces of study you can do to look at what might have happened before this event where the universe was opaque and dense, because again, this is not at the origin of the universe. This is just when the universe is so dense the light can't travel freely through it. So there are some things that you can do to analyze what's going on. The first one you can do is look at this spectroscopically and try to see if the temperature, remember the blackbody curve, the continuous spectrum curve, the temperature we get for this matches the predictions. According to our understanding of basic physics, the temperature of this should be about 2.73 degrees Kelvin. If I look at the spectral variations over wavelength, this is the wavelength in millimeters going this way. This is the intensity. And if I look at the blackbody spectrum, the predicted value of 2.7 is the red line, and the data points are measurements from our satellites. So this is a near perfect match of prediction to theory. So now we've got three pieces of evidence that we have an origin, and one of them is allowing us to do predictive stuff. But there's even cooler stuff you can do with this. If you go back to looking at this picture right here, you can see that there's some variations in the temperatures, right? There's variations in the temperatures here, variations, and those variations have different size scales. You see here's a big variation here, and here's a little variation here. So I can look at the variations of the size scales of these things and how the sizes, how the frequency of different sizes vary is something that is predicted by my various models of the Big Bang. So this is a graph showing a measure of how frequent, this D value over here is basically a measure of the frequency, or how often, how often that particular size scale happens. And then here are the different size scales. And the green line is what is predicted by the theory of the Big Bang. It predicts that we should have the maximum number of blobs on that chart at about the 1 degree scale, and the data are from our satellite measurements. So again, we're finding very good agreement with the physics that describes this event and what we're actually seeing. So if we look at these variations, again, these are microkelvin, very small variations in temperature in this graph. And the problem with that is that this is the entire universe, right? I mean, we're basically looking at, in every single direction, a uniform temperature to the sky. The only way that's possible is if this part of the sky somehow knew something about this part of the sky early on. That's the only way for them to be in thermal equilibrium, to be at the same temperature. So that tells us that at some point in the distant past, this piece of the universe had to be at near the same spot as this piece. The problem with that is that the time it takes for the universe to expand, if I just run back the clock, I can never get these guys close enough to be in thermal equilibrium just using that constant expansion rate that was measured by Hubble. So there's an additional feature to this model where in the very early instances of the universe's beginning, it inflationarily expanded at a rapid rate, even faster than the speed of light. Now this was an idea that was put forth as an explanation for why this side of the universe might have the same temperature as this side of the universe, but there was no direct evidence of this. That direct evidence was just discovered a few days ago in variations in the very subtle details of how this light is interacting as it travels through the universe. We have found evidence of this inflationary period. So there's a lot of stuff we can learn from looking at the cosmic microwave background that tells us that our idea about the origin of the universe is on the right track. Okay, so that's 3 pieces of evidence. We've got the universal expansion, the Obelisk Paradox, the cosmic microwave background, and as far as I'm concerned, we don't really need any more evidence. I'm sold on this this Big Bang idea, but we have one other one, and this is an important one because it's the thing that sets the universe up for star formation, planet formation, people formation, all the way down the line, and that is the Big Bang predicts the ratio of hydrogen to helium. The exact temperature and pressure early on in the Big Bang, the timing of the inflation and the expansion all set the hydrogen to helium ratio. And if we use the parameters in the model that match the cosmic microwave background and then look at what happens to the hydrogen and helium ratio, we see that the Big Bang theory predicts 75% helium, hydrogen, 25% helium by mass. This is something that we can then go look at our observations of primordial gases, and they match. That's the primordial hydrogen to helium ratio of the universe. So there are the 4 pieces of evidence for why we think the universe had an origin, and in particular why we think the origin was the Big Bang.